All right. So here's the plan today. We're going to do some practice with hydration and hydrogenation. Then we're going to add maybe as many as 4 new reactions. Okay. None of them have mechanisms that are as in depth as the last two we did. So for the most part, they'll go faster. And once you get the hang of learning new reactions, is the whole point of these new reactions is always just find your functional group that's going to react and then look at the clues and say, okay, I know what this type of reaction is. Right. So we'll go through the mechanisms, but we won't spend as much time as we did on the last couple lectures. But let's start with a little bit of recap. Compound A, this is actually a pretty common way of figuring out what something is, especially a natural product, is especially before the days of NMR and mass spec was basically, well, I don't know what this compound is, but I know that it reacts to make this. So what did I start from? So if we have compound A, and we know the formula was C5H10, and when it goes through the hydrogenation, followed by oxidation, this is the product we get. What did we start with? What does hydrogenation do?
It breaks the double bond.
Good.
Adds an OH.
And adds an OH. Where does it add the OH?
Lisa.
It's anti-Markovnikov, so it's going to put it in the least substituted spot. So we know that this carbon was one of the carbons called the pi bonds. So what does the other carbon have to be then? There's only one other carbon it's attached to, right? So we must have started from this molecule. 2-methyl-1-butene. So 2-methyl-1-butene reacted to make 2-methyl-1-butanol. If we started from this molecule and we put it through the oxymercuration reaction instead, what would we get? Pi bond goes away.
Yes. We get an OH.
We get an OH again. It's also a hydration reaction. So we break a pi bond, add an OH. Where do we add this OH? Most substituted. So this is our Markovnikov hydration. Hydroborations are anti-Markovnikov hydration.
Hydrogenation is substituted. That's just
Hydrobromation, you put the bromine on the most substituted again. So hydrobromation is also Markovnikov so far. You know how this works, Taylor. We teach you the normal cases, then we teach you the exceptions. All right, let's just do a couple practice problems. Just writing the products, not doing the mechanisms. But you can if you want. What does that really mean?
Like steps.
Well, you can think of it that way, but when you say H3O plus, it's really just water, acidic water, right?
Yeah.
So it's gonna be acid catalyzed. So acid catalyzed inhibition, it's the same thing, except allows for rearrangement if necessary. Is there any rearrangement necessary in this one? Intermediate look like that, and it's already a tertiary carbon.
I think one of the here on ones is
Most. The general rule of our common cause rule is you're putting your nucleophile goes most substitute. So far, the only mechanism we have that doesn't follow that rule is this one. Everything else is gonna follow our common. Hydroboration. You got it backwards.
no, yeah,
Hydroboration, you gotta be careful, hydroboration is anything we're talking about, hydrobromination is Markov.
And so hydroboration,
Boration,
what?
as in boron, there's your clue. If it's got boron involved in the first step, that's hydroboration.
But then everything else is the most sensitive.
Is most substituted.
So, the the AOC.
Yep. It's got a mercury in it. I break down the words.
Right. Is electrophilic addition included in this?
That's this one, right? B. I just stick to acid catalyzed hydrogenation because it's really two steps, break the pi bond and nucleophile. That's calling it electrophilic addition. It's technically correct, the overall process, but it's a little bit oversimplified. Technically, both of these are electrophilic addition.
Okay.
One's a hydration reaction, the other one's hydrogenation, but they use the same method. So the only difference is in both cases, you start with the acid catalyzed part, where the pi bond gets broken, and then that leaves a carbon cation. It gets attacked by a nucleophile. Do we have to worry about stereochemistry?
And which ones?
Any of
All of them?
We always want to be. Hopefully, our answer is usually it's not a big deal, it's often get worried, but occasionally it is. So in this case, we need to worry about it. No, there's no ring in the where we are adding the oxygen is not part of the ring structure. So it will go through syn addition, like we talked about. But because this carbon is not a chiral carbon, it's not a stereocenter, our final product doesn't matter. So if you wind up making a chiral carbon or your pi bond that you're breaking is part of a ring, that's when we need to worry about the stereochemistry. If we're not making any chiral carbons, no big deal.
And it would be like if you attach to a ring and there's something else also within it.
Right, because you have to have a frame of reference for it, right?
So like ring structures, you said it doesn't.
Ring structures matter. Especially when if it was the pi bond was here instead.
Because the ethyl's.
Because this gives us the point of context, right?
Right.
Especially if we had one of these and not the other one. Because then we can say, okay, are we adding it on the same side or opposite side? That's what we spent most of the second half of lecture on yesterday or Tuesday, hour yesterday.
Yeah.
So in this case, though, do we wind up making a chiral carbon?
In the second one or the first one?
Let's start with the first one.
Yeah.
No chiral carbon, we added an oxygen here, but there's also two hydrogens there, so it's not chiral. We added a hydrogen there, but both directions around the ring are the same. So it's not a chiral carbon either. We have to worry about this a little bit because when we go from sp2 to sp3, we're adding something, and sometimes we wind up making it more complicated by doing it, going from something flat to something 3D.
Right.
Did we make a chiral center here?
Thanks.
Right there, right? The other carbon is fine. We made a chiral center there. Is it gonna favor one enantiomer over the other?
Wouldn't it be that there's not?
Exactly. So just like with our SN1 reactions before, because it goes, if it starts flat, we can attack from either side. That mercury can get attached on top or it can get attached on bottom. So we're gonna make within sig figs, probably equal amounts of RMS, unless there's something else going on. We get to next quarter, we'll find that there actually is a way to do certain addition reactions and favor one enantiomer over the other, but we're not there yet. And that one guy in Nobel Prize for figuring that out. It is. We're gonna actually start getting into, especially when we get into next quarter, we're gonna get into people that won Nobel Prizes that are still alive. That guy who got a Nobel Prize for that. I studied one of his other reactions when I was in grad school. And he won a Nobel Prize for that just like 5 years ago. So he actually is he's only the third person to ever have won he's the third person to won 2 Nobel Prizes.
In the same time.
And his were both in chemistry. The other 2 were both at different topics. Marie Curie got physics and then chemistry. And then Linus Pauling got chemistry and then the Peace Prize. And then Barry Sharpless. Scripps, he's still working. Not only is he still alive, he's still working. And he's won 2 Nobel Prizes. And we get to study this. He's pretty.
He's just working.
He's working because he likes what he does. Yeah. When you win a Nobel Prize, you get $1,000 or $1 million bonus that goes with it. That you're supposed to put towards your research, but also any grants you write after that are basically guaranteed to get funded because you won a Nobel Prize. So, all right, let's look at the third one.
I think yes.
Where is it? Where is stereo set?
Well, okay, where we added the OH, right?
Yeah.
We have a branch, and then we have a ring that's going to be different.
Yeah, and then the hydrogen.
Yes.
No, there's no hydrogen.
Oh, no.
The
Yeah.
OH. Yeah. So if it was that, now it's not a stereo center because it's the same both ways around the ring. But here we are making a stereo center, so we're going to get if you do that, you can just write R plus S.
Okay.
If we had plenty of time and lots of space, we could write it out. We're going to make that, and then we're going to make the reverse where the oxygen's down and the branch.
Should show.
You could either write both of them. That's the way to most completely show your work, because then I know you're not guessing at where the stereo center is. But I'm going to trust that you all know how to count to 4 and figure out that it's a stereo center. Just this is a fancy eraser. I'm not used to fancy. It's got a little one, so I can erase parts of it without erasing the whole thing. Not all that effective though. All right, any stereo centers here?
Directly across.
Yeah. So this way and that way are going to give you the same thing. So no stereo centers. Did we had to worry about rearrangement? Was there any rearrangement that could actually happen? No, because our carbocation is already tertiary. The only possible time you could have a rearrangement if it's already a tertiary carbocation is if rearranging gives you another tertiary carbocation that also has resonance. That'd be the ultimate. If you could have a tertiary carbocation that's also got conjugated with a double bond, you could see that. Other than that, if it's tertiary, you don't need to worry about it. Then,
Well, like, I mean, it's the same route, but
this one is.
yeah, I feel like it is hetero.
Yeah, it's got an OH, a methyl, a hydrogen that's not shown, and then a cyclohexyl ring. Right, so this carbon is not chiral, but this one is.
Yeah. Should we do have series?
which means we do have a series. Chiral carbon means it's attached to four things, which means, yeah, exactly. Took a couple week break, but it's all coming back, right?
Definitely brush the dust off a little bit.
Let's do one that's the same thing but looks different.
Okay. Oh, I don't like how it looks. Can we?
This is a real biological molecule. This is responsible for the pine smell of pine needles and tops. Alpha pinene is, they call this a bicyclic structure. It's cyclic twice.
So it's like a ring attached to a ring.
It's, if you think about
What is it? A what?
bicyclic
I say what? Structure.
structure. So if you look at the carbons that I circled, that's a cyclohexene.
Yeah.
So the other way that you could draw this would be if you draw your cyclohexyl group flat, pi bonds. And have a carbon that's bridging between two pieces of it. You basically connected two parts of your cyclohexene over the top. Right, so, and then this carbon would then have the two metals attached to it. Or because that's also another cyclohexyl group, you basically have two cyclohexyls, right? That's why it's bicyclic. If we think of these ones as being the ones that we draw flat, and then we have our two methyls attached here. So sometimes it can be easier to redraw it. So basically, cyclohexene with an extra carbon bridging, what's that carbon? 1, 2, 3 to 5. It looks funky.
Yeah.
It's weird to think about in 3D. However, we do have your boxes. You can build this. Does it really matter as far as the reaction is?
Well, no, it's really have one double bond.
So only have one double bonds. So even though this redrawing this molecule is going to be a pain, at the end of the day, we're still going to be doing a hydration anti-microbial dog. So we're going to break the 5 bond, put an OH right there. Go and draw this. And it's going to be syn addition, right? So now because we have this ring structure and all this 3D shape, we do need to think about that. This one was syn addition, which means that OH and the hydrogen are pointing in the same direction. So if the OH is going down, that hydrogen we just added is going down, which means this methyl is coming up. And the reverse. Right, because we could get right, and the rest of the molecule is not going to be affected by that. So when we introduce the new stereocenters by doing these addition reactions, Typically, you want to just be careful to redraw everything in exactly the same spot except for where we're adding stuff. Because that's a hydrocarbon too, and so is that one. So we don't really want to mess with those carbons. You only want to mess with these carbons. So compounds like this, so this is actually similar, this shows up in a lot of different essential oils. There's a lot of essential oil components that look kind of like this, flavor compounds look kind of like this.
Okay.
Reactions like this are exactly why spices go bad, why they oxidize. Because if you let this get exposed to water in any sort of acidic environment, it can go through massive concentration. So over time, you're going to wind up with this molecule breaking down and be turned into something like this, which is not going to taste the same. So it depends. A lot of the specifics are going to be depending, but that's one of the reasons why, especially this is a really important and really prominent component in beers, coffee beers. Coffee beers go bad really quickly because of reactions like this.
Well, you put it in liquid.
And you put it in liquid and beer is acidic. Not a lot acidic, but enough acidic.
Yeah.
So you wind up with it making a ton of other products. So you've also got ethanol around it, the nucleophile and things like that. But it winds up being significant in that we see, and we'll see there's one other really common reaction that happens to alkenes that just involves oxidation. It's just oxygen. And any ground spices, the more you open them and close them, the faster they go bad. It's not just that you're letting the good smelling stuff out, it's also that you're introducing oxygen every time you do that.
What about like two different metals rub on each other?
So that's a different form of oxidation, metal oxidation. But yeah, anytime you have two different metals in contact with each other, one of them is going to corrode. And that's pretty, you see that a lot. Most common place to see that is in water heaters. You see it a fair bit in plumbing because you use a different metal. If you have copper plumbing,
Right.
you use a different metal to seal it. It's called sweating copper. It's basically soldering though. And that uses a different metal. So over time, copper pipes degrade. And you see it really obviously if you look at where your hot water heater is connected to your water lines, because usually there's brass involved and usually there's some other stuff going on, some other metals. All right. What would be different if it went through acid catalyzed hydration or oxymercuration?
Where you add finishing.
Yeah, both of these are our carbon composition, right? So we're going to put the OH on the carbon that has the methyl group in that case.
And how do you know if it's not acid catalyzed?
If it just says either just H3O plus as your reactant, or if it says H2O, H2SO4. Can we say which of these is going to be favored? Are these going to be made at equal amounts?
One is having less space.
What?
Putting it together, I was really nervous. It's not.
Yeah. But especially when you consider that there's a pi bond involved that is flat. This whole thing is this part's flat, right? Which means that these pieces over here are all kind of strained, pushing on each other. If we have to bring in the boron to form this reaction, and then just think about our mechanism. We added the boron to the less substituted carbon because of the stereos, right? So I'm just going back to this one. Since that's the one we spent more time on. We know that's how it works a little bit better. Borage.
Which is anti-Markovitch.
Anti-Markovitch, because the boron, when it first attaches, it comes to the less substituted carbon. It's one more. All right, so that looks like what we have up there, right? Ish. So actually, I can get closer. So our boron is going to come to the less substituted carbon to attach because of the stereos. We still have to choose, does it come from this side or this side, right?
Right. But with
so the boron's going to come here from this side. The boron comes here, and then everything maintains, all those steps in the hydroboration mechanism maintain that same stereochemistry. If the boron is going to attach from the bottom, it's going to attach on the side that has, we're going to wind up with our oxygen pointing down away from these. And this methyl is going to point upward. So this is going to be a more common, where we'd expect to see this in higher amounts. We're going to see measurable amounts of both, but if we really dig into it and think about the mechanism, this one is going to show up more often. It's the reason why we spend so much time on cyclohexane, thinking about these things in 3D, right? All right. And we'll see something similar as well with the oxymercuration. Because remember, oxymercuration, the first step was your mercury constant. It's that 3-sided ring. That's really going to be heavily stereos, right? So your mercury is going to come from the bottom, and then that means your oxygen is going to come in and attach more substituted side from the top. So we would more specifically or more accurately see the OH towards the other methyls and the methyl going down. So when we did that.
we commented on food things first. Oxymercuration is the AOC. Is there a difference between oxymercuration and oxymercuration demercuration?
No, I'm just, the demercuration is the second step. Just like hydroboration is technically a hydroboration oxidation. I'm just going fast and not being dirty.
And it would always be with the demercury.
Yeah, we never really saw at
But
oxymercuration.
like it wouldn't be something.
Right, it's not something else. All right, how do we feel about these?
Okay.
We've got kind of 4 reactions. Really, this one is the same as this one, same mechanism anyway.
Yeah. All right, please now. HBr and HBr.
It's the same mechanism, so I'm calling them the same thing. They're correct. It's 2 different ways of describing the same thing. Electrophilic just means it's drawn to that electron density. Acid catalyzed just telling you that your first step is to break the pi bond with an H plus.
So it would be Connie Taylor or my sister. It'd be the same thing.
It's to extend that analogy. My daughter has two brothers, right?
Right.
Saying electrophilic addition is like if my daughter says my brother. You know, it's one of two things that are functionally very similar, but they're also not entirely the same because electrophilic addition could be hydration or it could be hydrogenation. Right, so they both fit under that umbrella. But now I'm splitting hairs and overextending an analogy. All right. Let's add another one. So this actually has a really, really interesting, might be overselling it, but it has an interesting backstory a little bit. They could not figure out what was going on. The first time this mechanism was published. So this is just our electrophilic addition, catalyzed hydrogenation. This got published by Markovnikov, and then somebody in Germany tried to replicate it, as you do, except that they kept getting the anti-Markovnikov product, and they could not figure out why. They went through the, they didn't call out Markovnikov for fabricated data, but they got together like, well, how come you're getting this result and we're not? We're getting the anti-Markovnikov result. And it turns out it was because their hydrobromic acid was contaminated. I want to say it was with peroxide. Because what happened, what they eventually figured out was happening, is that if you do the same reaction, but under conditions that favor a radical forming, you actually get the anti-Markovnikov product. So, under normal acid catalyzed reaction or conditions, we form the Markovnikov product. We put the bromine on the more substituted carbon. If we do this in the presence of hydrogen peroxide and a little bit of light, we get the anti-Markovnikov reaction form. And this is going to be the first time I introduce another style of arrows.
Yeah, they only have like one thing.
We call that a barb, like a barb on a fish hook. One barb means only one electron.
Okay.
So usually we draw two barbs because for the most part, okay, and we're talking about hair split.
Yeah.
If it's only a single electron moving, we only draw one barb.
So we should be really clear and forward if we want to.
Mm-hmm. Right, and this is going to be the only time that you're allowed to draw two electrons moving towards each other.
Yeah, what does that mean? Like it happens later.
So basically, this is forming a new bond. If you only have one electron coming from the propene, to form a new bond, bonds are two electrons. So basically, one electron from the propene meets up with the one electron from the bromine. And they overlap and form a bond. You have to have that overlap, so we have to have two electrons to form a bond.
Yeah.
So this is the one time you're allowed to show electrons moving towards other electrons.
Is this like the only time it actually happens, or just like for our knowledge, this is?
This is radical reactions is a different set of reaction steps. So our mechanism steps so far have all been, it was what? Nucleophilic attack, leaving group leaves, proton transfer, rearrangement.
Yeah.
When we bring in radical reactions, we're gonna have a new set. For now, this is the only one I'm gonna show you for right now. So we don't need to worry about it in too much depth.
This is something different. But it's anti-mark, so it's in. Well, that's true. So you just say that. So what is it? Radical.
Radical HBr, or radical hydrogenation.
So it's one from the pi bond goes and makes the lone pair, and the other one makes the bond.
And it's not really making a lone pairs, it's not a pair. So it's a radical.
Okay.
So anytime you have an unpaired electron, we call that a radical.
Well, we always have to be given the thought, the arrow.
Let me see the way that it's written. I know I have a summary.
Is it at right in the dot? It's
No, because that's just saying in THF.
As the solvent. So it's generally written as, I don't know why I don't have it written here.
If you do propene, HBr, comma, H2O2. You need something to start the process. And hydrogen peroxide is the most common way to start a radical reaction because if you shine light on it, then shining visible light on hydrogen peroxide causes it to split up into radicals, which initiates this whole process.
that's why like it comes in the graph.
Exactly. I have the same thing too, right? Iodine and hydrogen peroxide are both heavily sensitive to light because if you shine visible or UV light on them, they break up into radicals.
Well, like, okay, in the case of hydrogen, right, it's in the little like tinted glass bottle and you take it out, and but then once you take it out on like a tip or something, does it immediately start?
Not immediately.
Okay.
It will start splitting up faster here at high altitude because our sunlight is more intense. That's H nu. That's the Greek letter nu. Remember light? That's energy of a photon. It's going back to quantum in Gen Chem and in physics.
Both like 2 years.
So H was Planck's constant. And then nu. It's actually here's a good tip for you. Greek letters are actually in the dictionary, and which means you can use them in Scrabble. So nu is actually a really good way that you can score a whole bunch of points because it allows you to count in 2 directions. Same with XI.
We have plays around. This is Scrabble.
That's fair.
I'm purpose.
All right, at break time, we'll do a crash course on how to really piss off your friends and family when you play Scrabble with them.
Okay.
My
Yep.
Laura's grandma stopped playing Scrabble with me towards the end of her life.
She was like, this is the last straw.
Because she likes to win. And one of the last times she played against me, I got 2 7-tile words, same game.
Okay.
Which is a bonus 50 points. You can do that. And so I basically had 1 and 2 turns. Game was over. And she bragged about me to her friends,
Right.
but she wouldn't play me anymore.
Yeah.
Laura stopped playing me too.
Yeah.
That's okay. We don't need to play. We play cooperative games in our house now. All right.
let's look at one more reaction here. Sorry, I guess one more thing about these radical reactions wind up being really useful in a lot of cases because they're self-catalyzing. Once they start, they continue till everything's gone. Because if you look at what we started with, we started with a bromine radical that reacted to form a more stable radical, but it's still a radical, which means it's not stable, which then grabs a hydrogen from another HBr and makes another bromine radical. So we end making more of what we started with. We'll see that this is actually a really common thing to have happen in polymerization reactions when we make plastics. Because you can basically start the process by shining a little bit of light on it to get it going. And then you just let it go and it goes and goes and goes until it's done at that point. There's neither of you surf, do you?
Not really.
So if you get a ding in a surfboard in the fiberglass,
Yeah.
the way that you replace it is with this stuff called Solares, which is basically you take this epoxy that cures when you shine light on it. And you mix these two things, two tubes together, and you put it over the ding and you flatten it as best you can. Then you just put it in the sun for about 10 minutes. And it's a very similar reaction to this that causes it to basically turn into one giant molecule. Yes. Because you're not working with fiberglass, you're working with other stuff that slides on the snow better. Fiberglass doesn't slide on the snow very well. All right. Last reaction before we take a break. It's called hydrogenation or catalytic hydrogenation. And it's catalytic hydrogenation because you need a catalyst. Turns out you're going to add the same thing to both sides of the pi bond. So it's neither or it's both. If it's a symmetrical reaction, it doesn't really matter, right?
Now you can high chart.
Right, so because we're going to start by, we just go through this process where you wind up adding one hydrogen to each side. Break the pi bond, you add a hydrogen to each side. So it's still addition. All of our addition reactions work. Break a pi bond, add something to each side. It's just in this case, what you're adding to both sides is the same thing. So you can't tell the difference.
So like if H2, you add one hydrogen to each side.
Correct. And you have to have a catalyst. If you try to do this reaction without a catalyst, you have to do it at like 400 atmospheres and 150 Celsius. So it'll happen if you put it under really, really intense conditions. But for the most part, we just use a catalyst.
But it's like
PT is, what is PT on the periodic table? You know this one. It's right next to gold. Platinum.
good job.
So we'll find out that a lot of precious metals, very expensive metals, wind up being used as catalysts. They're expensive metals mostly because they don't oxidize easily, which means that they provide a clean surface for stuff to stick to. So if you look at what's in a catalytic converter, catalytic converters are called catalytic converters because they catalyze similar reactions to this. And one of the main components in a catalytic converter is platinum. You cut open a catalytic converter, it's basically like a hexagonal spider web filled with these wires because they're trying to maximize surface area while using as little of this stuff as possible because it's expensive. And they're also called trimetallic converters because they're three very expensive metals. It's platinum, rhodium, and
See the periodic table real quick. It's sound like platinum, rhodium, and osmium, maybe. Basically, three metals that are not very reactive in oxygen that cause the components that make up smog to react more. All right, so what do we need to know about the mechanism for this one? Basically, that you only get syn addition. When you do this, the hydrogens always get added on the same side. So we can get both of them up, or both of our hydrogens added coming up, or both of our hydrogens going down. But we're not going to get anti-addition. We're not going to get them the hydrogens added on opposite directions. And it turns out that most reactions that are catalyzed by a solid, by a surface, have this property. Because the actual mechanism is basically you have a platinum surface, it's a whole bunch of platinum atoms. You expose it to hydrogen gas, the hydrogen gas sticks to the surface. When it sticks to the surface, basically the platinum, the extra electrons from hydrogen and from this alkene are going to stick to that surface. And if they're all stuck to the surface, they're all kind of already oriented the same direction. So you wind up with the first step is your alkene comes in here and one of these hydrogens sits one side, but then the other carbon is also stuck to the surface. And then another hydrogen adds to it and breaks off. So the net result is it's always adding them in this going in the same direction. And this is not a mechanism that I asked you about. I'm just explaining why it's always syn and why we need the catalyst. We need the catalyst to start this process of breaking these hydrogen bonds. Otherwise, there's not enough of a favorable energy to be worth breaking up these bonds and starting a whole process. All right. Let's take a break. Come back at 5 after.
We didn't work early. It's not been so good yesterday. It's not time to be off today. So they have like a See this, three, well, technically I got five, four, five, I got five. Was it with the deal? Yeah. But that's also because his credit card stopped working when we were in New York. So he like went to pay it and then I wasn't going through because we're here and there. So I really only got it free. What was it like? It was, yeah. I only really got it free. But then because I had to pay for the two that, the one that he was getting, that's for the one free. So then I got another one for free. $100 for a shirt. Yeah, but then one was free.
Have you seen prices? That's not actually that outrageous for,
And-
for 4 shirts for $100.
No,
Oh,
they're like,
Oh.
they're like suit shirts.
that's actually not bad either if they
And
fit well.
it's a brand that's made by I think it was actually a professional hockey player. So like a lot of professional athletes go there because it's like their game day suits sort of stuff. I think they're nice. They look nice. You can look someone about. Is a picture right now. I always have to make the cheese because I was young. It's one slice of cheese. It's one slice of cheese. We were. But I'm like, do you see how like his shirt is like, it's not X's, it's like papers and something else. And she was like, yeah, like he needs better shirts. So I was telling her places you could go to get better, nicer shirts.
Yeah,
I first said Sierra and she goes, Sierra's expensive. And I said, well, no.
I think you had actually, it's you're not guaranteed to find anything, but TJ Maxx is probably your best option up here.
Yes.
You just have to be willing to not buy something if there's not something that fits.
And we might just. I like Sierra for making my summer shirts, because they're all like, the like Hawaii pattern, yeah, cotton, button down. And we farm shirts. Farm shirts, and I last I did check the shirt of the farm. Yeah, the farm doesn't fit shirts, it's true too. I wonder if Target would have it. They're not all the photos.
No different than Sierra.
Yeah. You just gotta find who ones. This lotion is really thick, it's like not in. I keep rubbing it, it's not going anywhere.
I hate putting lotion on my hands for that reason. They just feel greasy for the rest of the day.
I should put the bonds fixed though. I've seen those and then I can do that and then I will.
So my father-in-law has he has a lot of joint issues because he played hockey for 60 years of his life. Yeah, he actually got, you know who Herb Brooks is? He was he would. He was the coach of the Miracle on Ice team in 1980. Herb Brooks. No, my father-in-law got cut by him at the University of Minnesota. One of his claim to fame. But anyway, he has they actually make those roll-on lotion sticks with CBD and THC in them for people that have joint issues. And he has to use that on his neck and his hip.
Yeah. Something's sitting in the back. Yeah, whose hand's that? I think it's Chloe's. She forgot that because the toothbrush is still there. Well, it's not for now. So it's got to use on the lotion. I think she forgot to keep it. I was surprised. And then I took one out, but it didn't say anything about it. Please,
Life skills. Let's talk about Scrabble for a second. Then we'll do more reactions. So you know the premise of Scrabble, right?
Yeah.
Spell words. So, however, you only get any words that you make, you get to count points for them.
Right.
Right. So, and the more rare, the harder the letter is, the more points that letter is worth.
Okay.
So if you spell the word like, detox, that's got an X in it. X is 8 points. Vowels are only 1 point, and these T is 1 point. I think it is 2. There's also, so these have to fit into little boxes. And if you happen to put them in the right spot, then you get bonuses. Like it might be a double word box. Means that you double the number of points you get for that word.
And we start Scrabble, so we'll put a letter down.
Basically, you start by drawing 7 letter tiles, and then you just have an open board, and you have to start. Do I still have that? There's a knockoff version called Words with Friends it's basically just Scrabble except the bonuses are in different spots and the point values are slightly different so that they don't get sued. But you basically this A right in the middle is on a star pad. Star, the first person who plays has to play there.
Okay.
And now if you double, PW is double word, PL is double letter, etc. So where the Greek letters come in is that if you play a 2-letter word, you can actually play you can actually count in both directions. So let's say I had, if I wanted to play Civ, because those are the tiles that I have in front of me. Actually, that's, or let's just say Ring. Yeah, so what I have to connect to this one. If this was the first word played, I then have to connect to it. I can then play Ring like this because I get or XI is a Greek letter. Psi is a Greek letter. So I get to count OR, so that's only 2 points, but then I get to count XI, which is going to be another 9 points, plus I get to count RI and G. So playing two directions at once makes Scrabble players that aren't used to it very upset. And that's where the Greek letters, 2-letter words are really, really useful because you can do that. So new, mu, mu is a Greek letter as well. If you look at Scrabble dictionary, you'll also say that FA is an abbreviation of pizza. So,
Okay.
so that's a really common one because it lets you count Z twice, right? Anyway, so Greek letters useful in Scrabble and similar games.
Yes. I've done it so long, that was actually great. It like singles all the way down there.
All right, let's add another reaction. Halogenation is similar to hydrogenation in that it's symmetric. We're going to have the same thing on both sides. So this is another one where Markovnikov versus anti doesn't make a difference. Doesn't apply. So I guess if you're keeping track, this should be a T chart. I see what you're saying with the pie chart. Not like this. You can have Markovnikov, anti, or neither. Slash both. This is going to be another neither slash both. Because anytime it's symmetrical, we're adding the same thing on both sides. You can't tell what I added where.
Right.
All right, so in this case, the halogenation, it doesn't need to be catalyzed because the halogen gases are already reactive enough. Hydrogen's not reactive enough to react without the catalyst, but chlorine and bromine are. We only really are going to see this with chlorine and bromine because chlorine is too reactive and then iodine's not reactive enough. So with chlorine or bromine, the way that we're going to see it show up is just that you have an alkene and it's just Cl2. If you do that, all you have to do is expose an alkene to chlorine and you're going to get this reaction. It happens pretty quickly. We're going to do this with bromine where we have to catalyze it a little bit. We're going to catalyze it by shining just a little bit of light on it.
Okay.
To start the process. Actually, that's a different reaction. It's a free radical reaction. Never mind. We're going to do it differently with bromine. And what we see with this reaction is that we only get anti-addition. So anti means they're adding opposite sides. We do this to a cycloalkene. We get the bromines trans relative to each other only.
Okay.
Which is similar to what we saw with mercury, right? The oxymercuration is that the oxygen only got added anti to the mercury because it was basically doing an SN2 attack, right?
Wait, so this is with the rings or with the bromine? Like, what's the specificness to it?
Specificity.
Yep.
So
you see how the bromines, we didn't break the ring structure up, but one of the bromines is up and one's down. You will never have this reaction happen where both bromines are up.
And then to know what will happen, it'll either be BR2 or CO2.
Correct. So if we're looking at mechanisms, does this mechanism make sense? You got extra electrons in the pi bond, you can send those electrons to the bromine, the other bromine can take the electrons away. And we get bromide, which we know is relatively stable in a decent nucleophile. And then bromine here, and then a carbocation. And then the second step would be what?
No, that can drive transfer.
Yeah, nucleophilic attack. Would that make sense?
Yeah.
Why?
It's that side with the other one.
Yeah, it looks familiar. If we only see anti-addition though. Let's look at it. With that cyclohexene. So we said that second was electrons, the pi bond attacks bromine, the first bromine, the second bromine takes the extra electrons. So we see a bromine here, carbocation here, and then bromide, which could then attack the second slide.
And it's not going.
Why?
That's what we just learned.
You know it only has anti. Is there any reason why we only see anti though? If it goes through this process, we're asking if this mechanism is plausible, but I'm not telling you the mechanism. Bro, the second step should be able to add on either side, right?
Well, rings aren't flat.
Rings aren't flat, and there is some sterics involved, but we should say measurable amounts of both the cis and the trans in this case. That's not what we see. So all that to say, just because I put a mechanism on the board doesn't mean it's right. So they were able to figure this out. They knew the researchers figuring this out, and that was their first guess. Was the same mechanism is true. But as soon as they realized that you only see anti, they realized that can't be right. Because if it's we only see anti, this is planar still, right? This is flat.
Yeah.
There should be equal probability of adding top and bottom. So something else has to be happening. Right, so if it was going through this, we should see some sin addition. Well, the sterics might see that it's mostly.
So the answer is no.
So the answer is no. So they went back to the drawing board. In the first step, what's kind of similar to what they saw is that because it's a large enough molecule, it actually makes that three-sided ring structure similar to the mercury.
So
Are we talking about the T-chart? It is neither Markov nor anti.
what's this? This is in addition, not Markov. The easiest said it was.
The mechanism that I drew is so Markov versus the anti has to do with where we put one of the pieces, right?
I'm saying this one's neither because we're adding the same piece to both sides. We're adding bromine to both sides, so you can't tell. So Markov-Markov versus anti-Markov-Markov doesn't make any sense.
But it is still a mechanism.
Yes, exactly.
This is my view, it's just something big, like, you shouldn't leave it, it's nature, you leave it.
In fairness, I asked if it was plausible, and you said, well, I guess so, because you drew it. So the net result of this, what they figured out though, is that we still get something, it looks very similar to that oxymercuration first step. Where you get one of the lone pairs from the bromine comes down and attaches to a carbon. The pi bond goes to the same bromine. And then the other bromine basically leaves to make bromine. So we get this three-sided ring structure, which is the same thing we saw in the mechanism for oxymercuration, right? Except it was a mercury instead of bromine. A really common pattern in mechanisms is if you make a three-sided ring, it's not stable. So your next step is going to be to attack from the other side and break that three-sided ring. So this is just like the oxymercuration, except instead of mercury making three-sided ring and then an oxygen coming in from the far side, breaking, we have bromine making a three-sided ring and then another bromine break. I'm not.
Lone pair on the protein in this second step doesn't attack this other bromine, it attacks the bond.
It attacks the carbon. Because this carbon, a carbon bromine bond, bromine's more like negative than carbon, right? So basically there's a partial positive on this carbon. So your bromine is going to come in and attack carbon, which allows this strain bonds to break. So it's effectively doing an SN2. That's kind of the way you think about this.
Or at least keep that. At the very end.
An enantiomer. So basically you're gonna get this, and then you're also gonna get the mirror image. They have to be opposite of each other, but that still won't give you an R versus an X. So, fun fact. My OChem instructor was in grad school. He was in the same when he was in grad school, not he was my instructor in grad school. When he was in grad school, he was in the research group that demonstrated this. Which now you're 2 degrees removed, but your instructor's instructor helped work on this.
Yeah.
And now it's in textbooks. This is a really common one to show up. This shows up any standardized test that's going to have OChem in it. There's a 50-50 chance this is going to be one of the questions. Something along these lines. Because these addition reactions are some of the first real complicated mechanisms that you learn. And there's a lot of flexibility to them. All right, so if we can have, if first step is we make this three-sided bromonium ion, three-sided ring. And then the second step is second bromine comes in to attach. Could we swap out this nucleophile? It's just an SN2, right? So anything that can go through it, that can be a nucleophile and an SN2 can do this. So now we get to classify it as Markovnikov or anti.
Okay.
Because if we do a similar reaction, so we do this when water's around too.
So this is the one that's either.
Yes. So the first step is your bromine gets added. You make that three-sided ring. The second step is your water comes in to attach, right? So if this is our molecule, our intermediate, our first intermediate is going to look like and then say that CH3 into the board, into CH3. Let's draw these ones flat. Okay, so I took this molecule and I rotated it so that we can see that the bromine is attacking from the top.
Okay.
Second step is water comes in and it's either going to attach there or there. What did we see when we saw the same type of mechanism with mercury and then water as the nucleophile? The mercury also made the three-sided ring. Where did the water attach?
I have an answer.
Or you can think about it in terms of, was it Markovnikov or anti? Markovnikov. The only anti one, hydrogenation, radical hydrogenation, or hydrogenation.
Wait, there's two what? Hydrogenation. Yeah, right, we just learned about. This one. Which is also just hydrogen. Radical hydrogen from a pitch. Okay, but it also. What's the thing with the base letter? And then it's not a weed. I didn't know where it comes from. And then I bought something more for scrap. Okay. Then we have two in matters.
All right, so the oxymercuration was Markovnikov. Because the second step was water attaches to the more substituted carbon, right? Because that bond between the more substituted carbon and the mercury was weaker for several reasons. We would expect to see the same thing here. This one's also, you could call this one Markovnikov because the second step is your oxygen attaches to the more substituted carbon.
So it is.
Yep. Because the mechanism looks a lot like oxymercuration, just without mercury.
So what's the indicator?
If it's bromine, Br2, and with water around. If it's just bromine reacting, then it doesn't matter. It's neither Markovnikov nor anti because we're going to add a bromine to both sides.
And would water always be?
And water's always going to come from the opposite side. It's the same mechanism as the bromination, except where the second step is water attacks instead of bromine attacks. Right, and this gives, we're gonna start seeing weirder functional groups that are combinations of other functional groups now. This is an alcohol and a bromide, right? If you have an alcohol next to a bromide, say one carbon away, they call that a halohydrin.
That's,
There you go. Yeah, so halohydrin formation is just gonna be halogen, either chlorine or bromine, mostly bromine, with water around too. Okay. If you don't have the water around, if you just have the bromine, you add bromine to each side.
right,
If you have the bromine, but you also have something else, you get a competing reaction showing up. Because you also have water that can come in that second step. And so basically, the halohydrin formation is just swapping that with water. Right?
when we're attaching it to both sides. And like we have the, like on the next side of the. Like B with the three, yeah, is it gonna go like on one end of the bond and then like coming. Like on the same side, but just down, or is it gonna go like where the OH is? Does that make sense?
If we're gonna go, if this one, we didn't have this here. When we do the halogenation, it's still an addition reaction, which means you break the 5 bond, add something to each side. So it's gonna be, if we put a bromine here, let me just. We'll just blank that out. We just had that. First step is gonna be. We make that very three-sided ring, bromonium ion. So, and then bromide, and then the second step is going to be. We're just drawing the mechanism for it, was just doing bromination.
Oh, so that's the three-sided, okay,
Right, so this is the three-sided one, this is gonna come from the opposite side on the more substituted carbon.
I don't understand how. The. Like one of the bonds goes with the bromine. But then it still stays in the same. Spot, kind of, like. I don't know, getting my head around like which. It stays there, but it doesn't stay there, you know?
And. So let's build this molecule for the starting material, and then let's look at the shapes that we get. Alright, so here's our pi bonds. And here's our two metals. I have some in my office. I can, let me finish this up.
There's some tallies, those might be spent.
So when this comes in here, first thing it does is it's gonna break this pi bond.
Yeah.
And it brings its own pair of electrons
But yeah,
to make this unstable three-sided one. There's not even a second hole here.
yeah,
So then we have this. Second bromide then is gonna come in and attached from behind because it's bringing its own electrons.
Right.
So let me just give it its own electrons. We've got this shape. This comes in from the on the more substituted side. But you have to be really about spot to put this. So thing.
One of them.
One of them breaks. The bromine, actually, you know what? So we have this.
Right.
This one comes in, breaks this one now attaches over here. It does an umbrella flip. Because it's an S2. So we get this. There's your final product. That's what I'm trying to draw here.
Yeah.
Okay? So the 3D, thinking about it in 3 dimensions will never let you down, but sometimes it gets more where it gets better.
And then it means those electrons back is what makes it neutral again.
Exactly. You started with 2 things that were neutral. And the mechanism that I didn't show was this lone pair attaches there at the same time as a lone pair. That way, the other bromine takes away a pair of electrons. So you get a bromine with 2 bonds, which gives it a positive charge, and a bromine with a negative charge. So it still adds up to 0. Right? Which is why the next step is then you. It's a good question.
Anyways.
Anyway. I don't. Autoplay. The sound is correct.
Oh.
That's not what it sounds.
It's really filling my ears. So lovely. Should we try
It's definitely the autoplay. We're turning it off. It'll go away. You know, it's air seeping somehow.
Yeah.
So it'll should get lower in intensity as the would think. All right. It's okay. We're almost done for today. If it doesn't silent, nobody wants to listen to that.
There's just 2 of us because it's garage.
It's true.
That's true.
There you go. I hear it. Coming down. The pitch changed a little bit. All right. So this is more the mechanism drawn in more detail. Not sure my office to be any better because I would say this exactly on the opposite side of the wall. My office is right here. So this is the same mechanism we just drew, but prettier. With the proton transfer, the last proton transfer section. So we know which carbon gets the alcohol because it's Markov. The more substituted carbon gets the alcohol because that's what's going to make things most stable. The bond between the bromine and the more substituted carbon is weaker. Partly because that carbon is more stable on its own, and partly because of the stericness. But for both, it's the same logic as with the oxymercuration. Right, the more substituted. Oh, it went up. You guys hear it? All right. So here's recap. This is all the mechanisms so far.
But this, we can make our chart. This
Yeah.
is question marks, not make questions, let's do a race.
We'll finish.
Use race. Yeah.
We'll finish this. We'll talk about this slide and then we'll be done for the week.
Okay.
And your quiz is just 8 reaction practices. You can upload just one picture for all of them. The first one we had was hydrogenation. HCl, so it's acid catalyzed addition. Smartkovnikov. It's anti and it's syn. Because you're gonna lose that stereochemistry because it's got that carbocation intermediate. And if we're keeping track, there it is. We have to pay attention to possible rearrangements. I just left off a whole syllable there. Rearrangements.
I told you my spelling keeps getting worse. So this is, what is it called?
So you could call this acid catalyzed hydrochlorination. Well, we did it with bromine before. It was acid catalyzed hydrobromination, but it's going to do the same thing. It's back.
It's like when you squeeze food, like, no, we just call it acid catalyzed nitrate.
If we do this with just H2O or with water and an acid, then it's acid catalyzed hydration. Same mechanism problem, same, it's still Markovnikov, still gonna get anti and syn, still possible rearrangements.
Or it's dry with the products.
Yes.
What do you? Inside this one part, we bring. Bringing this over. So it's like our meetings goes on the piece. Yeah.
Bingo.
So it's gonna be the upside down house with the angle. And
Sure.
the roofs on the left. And then the like next on the next carbon over, I think is where the OH is. Yay.
Only syn addition. So you're gonna get the trans product plus EN. This one, acid catalyzed electrophilic addition. Smarkovnikov, we're adding hydrogen to one side, chlorine to the other.
Yeah.
Chlorine.
Wait, this one's the acid catalyst. Oh.
Hydroboration.
It's gonna go on the less substitute. Oh, on the more substitute. Maybe I can go first. I can go ahead and this, okay?
Okay. It is. That autoclave is from the seventies, so it's not.
Really?
We've probably had that as long as the scholars exist.
It's never been replaced.
Not to look at.
Carl,
Have you seen it?
Have you seen it? Carl would like scrub the lights scale off. This
It looks like it was built, it looks like something out of Fallout.
Yeah, you've seen other things. Yeah, nothing like it. I was like, oh yeah, door, some buttons, no.
No
Big
buttons.
No button, no buttons, sometimes big hinge thing, like
Switch.
it just does one thing.
Yeah.
See, we're used to working in like the medical, so like ours can do like 5 different things, like ours can do like if you have a pack with the blue paper, or if you just have staples, or like surgery, like it, or loose, like it.
Well, when it's not behaving like this, ask to see it because it's fascinating piece of history.
It hinge thing. Oh, we don't understand something. Okay.
This one's our oxymercuration. Demercuration. Markovnikov. You get kind of anti-addition, we're gonna get both of them. Right, because we lose the stereochemistry when we do that demercuration step. First, go ahead.
Plus the other person who did it all about that.
Is this one down in the Dixiemer? No, there's both ways around the brain right now. Drawing a pentagon upside down should not be that much harder than drawing it regular, but it is today. So it's Markovnikov.
Yes, because when you have the inverted, it like goes on and then it goes to travel and then goes.
Yeah, bingo. See, the more we spend time with this, the more it's gonna make sense.
Doesn't work. That's an oxymercuration. Oxymercuration.
Good.
But.
The oxymercuration step is anti, so if we were drawing the intermediate. It would look like this plus En. But then the next step is we replace the mercury just with a hydrogen and we lose the stereochemistry. And now it's symmetrical both ways around. So it's not a stereo.
Yes, we did lucky. Okay. Next one.
Halohydrin. So that means you add bromine to one side. It's the most recent one we did.
Yeah.
Bromine goes to the more on the less substituted side, the oxygen on the more substituted side. And they have the oxygen and the bromine have to be trans relative to each other. Because it's only anti-addition. So that one's definitely gonna have its less again, because we had a lot of stereochemistry going on in that one now. Last one's the easiest one. Hydrogenation, you break a pi bond, you add hydrogen to both sides. So you just take it from being an alkene to an alkane. So I'm gonna draw it up above. Hydrogenation. Hydrogenation. Same reaction you see with partially hydrogenated soybean oil.
Okay. What is that react? What?
So soybean oil is what's called polyunsaturated, meaning it's got two alkenes in that fatty acid chain. You partially hydrogenate it, you don't get a fully saturated fat. You get something that tastes closer to a saturated fat than to an unsaturated fat. So you see partially hydrogenated soybean oil means it's the hydrogenation on one of the alkenes in that chain, but not both. It is. That's what they make the cream and Twinkies out of.
So it's very stable. Those last forever.
So in this case, we have, so we have a methyl and then also a hydrogen. And then on the right carbon.
Just two hydrogens.
But you only add one.
We're only adding one, this one
And
already.
to go the same.
The hydrogens you're adding have to go the same way. So if we had a way of telling where they would be added, they'd be added same. The hydrogens are gonna be on the same side relative to each other. So what's wrong with the molecules look like? I cannot be upside down. We just get this. And that's not gonna have a stereoisomer because both directions around the ring are identical.
Don't you have to try and do?
You can, technically, this answers the question, this is your product. If you want to show what you added, then you could say the ones that you added, if we did this, added a hydrogen into the board and a hydrogen into the board. It's not a stereoisomer though, because that ring is symmetric. Once you add the hydrogens.
So then how can we show that you also got?
It won't matter, it's the same molecule. So you don't need to show that then.
Only two of them have plus yet.
Only two of them have plus here.
Hydrogen, hydrogenation, acid catalyzed hydrogenation, 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 halogenation, and oxymercury.
I don't know why people struggle with it. It's not even complicated. No, it's absolutely complicated and it takes time to get used to.
Yeah, it's harder this quarter than last quarter, because there's so much that's the same but different.
Yeah, exactly.
So it's identifying each one as a little tricky.
That's why we have these weekend quizzes for you to work on. The one thing I'm not sure if it, last thing, it's not new, but remember when we had the anti-Markovnikov hydrobromination was when there was peroxide around.
Yeah, sure. You just have to put the guys that deal with your DNA.
Yeah, exactly. So the way that I don't remember if that's on the quiz or not, but if that's on the quiz, it might show up as. So let's do this for the same molecule. If you saw it as HBr, I said it's usually shown as hydrogen peroxide. But I'm remembering now it's actually more commonly shown as just generic peroxide. Brewer. Rur is, it's a anything, it means the same thing basically as this, except means that you can have something like carbons, you can have peroxide bonds within an organic compound.
But we have this HPR common H2O2 and over H20.
Over H2, yeah. So if you see this, it means the same thing.
Race.
Don't raise word.
Rur.
This whole thing. No, no. So. This. We break a tie bond. Wait, are we looking at the
Sure.
polar or the radical?
So this is this, the fact that it's got this tells you it's the radical.
Okay.
The polar version is just, it's just this, it's the same as this one. So it's Markov. This one does the same thing except anti-Markov if there's a peroxide around.
So it takes off the pi bond and attaches to the less substance.
Correct.
Am I have? It's probably three. I think it's like I have.
Puts back.
I'm drawing them differently than you. The way you're drawing it is true. I'm doing like.
This. Flip it around. It's probably easier to draw.
Yeah, I just did, well, no, I did like, you know how we draw the house with like flat curve? I'm doing that close now, so I'm doing like, the top is flat, down flat, then flat.
That's the easier way to draw it, and nobody's gonna confuse that. This is just a little bit close, I'm trying to get closer to those actual angles, but I'm messing up every time. And this one's gonna get all possible stereoisomers. Free radical mechanisms are not stereospecific because those radicals are flat. So you're gonna get the one that looks like the methyl. I'm gonna draw you. I can't handle it. You're gonna get methyl up, bromine up. You're gonna get methyl up, bromine down. You're gonna get methyl down, bromine down. Methyl down, bromine up. So they're actually getting 4 stereoisomers in this case, because you make 2 chiral carbons, and it's not specific at all about how that's done. So you're gonna get all possibilities.
I just had plus all stereos. Test
It would be it'd be a good practice problem to go through and see if you can draw or make sure you can. But we're already over time, so I'm not gonna do it now.
I know I keep forgetting, I'm not in the cycle again yet, you know? Well, we don't have a period. Well, I haven't gotten things to the being back then. I'm ready to be retired. So you know, I'm just like completely excited. Video spend my days. Yeah.
It does sound good sometimes, doesn't it? I'm just excited that I'm back to teaching all entirely here after next week. I'm not going to the high school anymore after their finals are next week.
But what about next quarter?
They're canceling the class over there because we can't staff it. I have too many students here in Chem 100. We have 55 students in Chem 100. We have to add another lab section. It's going to be Thursday afternoons. The last one is like, it's going to only have like 5 people in it, but we have 5 people on the wait list that need it to transfer this year.
Well, they
they did that for me for OCHEP last year. I was like, I needed to transfer up to Vibe, and one with some. I don't want to change it. It's like,
Okay, not sooner than 5.
it's good to do.
And that was an issue with the planning on the counseling side, which, sorry, but they can't. Right, but not at the same time. Usually most bio majors will take Gen Bio and Gen Chem at the same time. So we make sure those don't conflict, but we're still limited by our time, by the physical nature of the universe we live in. Right. That's an uncommon combination for a bio major. So that's what you ran into. Oh. All right. Y'all have a good weekend. I'll see you on Tuesday.